continuing on with our neurophysiology, specifically looking at resting membrane potential. Now, that term I was using before in the last video a little bit, as well as things like depolarization a little bit. What we need to do in this time is to go through what this actually means, explore the ideas a little more. So first off, resting membrane potential. In the case of most neurons, we're looking at negative 70 millivolts. Now, that is not an absolute number, as I mentioned. That is a relative number across the membrane. So what happens is the inside of the membrane is said to be negative 70 millivolts compared to the outside number. So just making up some random numbers. If the outside was 100 millivolts and the inside was 30 millivolts, that would be the negative 70 millivolts. Now, those are not real numbers, just made those up. Just trying to get the idea how the inside is just negative 70 millivolts compared to the outside. It's not an actual number. And that's said to be a polarized membrane because there's a difference in the charge, the polarity from the inside to outside. Now, this difference in charge, this polarity, is maintained and because of the various different ions. Things like sodium, potassium, chloride, different protein anions. These positive and negative charges are managed by your cells to stay in certain concentrations and certain levels to keep this charge difference, this potential difference across the membrane. Now, each one of these, each potassium and sodium and chloride and proteins, they all have different permeabilities, different channels that can open, different ways of moving across. And it's because they have different permeabilities and different control mechanisms. Your body can move one particular ion at a time. Only sodium's moving. Only potassium's moving. Only chloride's moving. So it can control which ion's moving to make sure it maintains this potential difference, this resting membrane potential, or if it wants to depolarize or repolarize, some terms we'll get to. So it's all about control. And all this is occurring at one point. So for example, right here, you can see how on the inside it's negative, outside it's positive of the membrane. The meter here is showing is measuring at one particular point. It's not measuring before or after it. It's just at that one single point. So you're seeing how this point right here is being measured. Over here is a reference saying, hey, that's what the outside fluid's like. But that's the measure on the inside. And it's 70 millivolts lower on the inside of the membrane compared to the outside. So looking at the actual ions you see here, you're going to notice that there's different concentrations of the different ions. For example, sodium. You can see how sodium here has a higher concentration on the cell exterior, so outside the cell. Sodium is going to want to rush into the cell if possible. You can notice that cell can diffuse a little bit through. Those are leakage channels, but it's not much. You can't do a whole lot of that there. Then you have potassium. Potassium has higher concentrations inside the cell. Potassium is going to want to diffuse out of the cell if possible. So those are two of the main ions. But we also have the negatives. Chloride, higher concentration outside. The anions from protein, higher concentration inside the cell. It's all these concentrations that balance each other out to make that resting membrane potential. Now you notice here, we're going to have this sodium-potassium pump. Now you can see with this sodium-potassium pump, how the sodium is all being pumped out to the cell exterior. That's going against the concentration gradient. The way this works is the sodium-potassium pump is an active transport. It's going to take ATP, and that ATP will give energy to the system that allows to push sodium out of the cell against its concentration gradient. At the same time, it does the same thing for potassium. Potassium goes into the cell against its concentration gradient. The whole idea is your body is trying to maintain these concentration gradients. The high sodium outside the cell, the high potassium levels inside the cell. So just another way of looking at it here. So if we look at initially only having leakage channels of potassium, well, that might be a little of an issue. Potassium just constantly leaks through. But then you add in the sodium channel, also leakage. Okay, now we're leaking in both directions. Except if there's nothing to counteract that, eventually you reach equilibrium across the membrane. We can't do that. Because if there's no concentration gradients for sodium or potassium, we can't create any action potentials. So we have to maintain that, which is where the sodium-potassium pump comes in. That sodium-potassium pump will push the ions against their concentration gradients, making sure to maintain the high levels of sodium outside, the high levels of potassium inside. All right, terms depolarization, repolarization, hyperpolarization. Kind of alluded a little to depolarization earlier, but let's look at what it really is. Depolarization is when the inside becomes less negative. Remember, negative 70 millivolts is our resting membrane potential. So if we depolarize, we go negative 70 to negative 69, negative 68, negative 67, 66, 65, 64, just keeps on going, less and less negative, all the way heading towards zero. And it can even go beyond zero, because that's less negative. So depolarization is when the inside is becoming less negative. Now, repolarization is the membrane returning to rest. So it's trying to go from that positive or that less negative environment back down to the negative 70 millivolts. Pretty much repolarization, re is redoing, is trying to repolarize the membrane. You're trying to undo all of the depolarization. So depolarization, less negative, repolarization, trying to go back to rest, trying to go back to negative 70 millivolts. The third one, the hyperpolarization. It's more negative than resting. Now, that means you're going to negative 71, negative 72, 73, 74, 75. You're going beyond the resting state. This could happen because you've overshot your repolarization, went too far. This could happen because the different neurotransmitters are trying to prevent a signal from occurring. So there's different reasons that you can hyperpolarize something. But hyperpolarization is going more negative than the resting state. You're going beyond the resting state. So here's a graph kind of showing the exact same thing. You'll notice that you're at resting state, negative 70. But then you have a signal that depolarizes. Depolarizing is going less negative. You can see how it's going up and then it hits threshold here, then really shoots up quickly. The idea is depolarization is going to try and create a less negative internal environment. While repolarization, you can see it coming back down. Repolarization is trying to get back to the resting state, trying to go back to negative 70. In this case, you can see it went a little too low. That's the hyperpolarization. Hyperpolarization went below or beyond the negative 70. Negative 73, negative 75, negative 80, or wherever beyond. But went past or below the negative 70 millivolts. So depolarization, going less negative. Repolarization, coming back to rest. Hyperpolarization, going beyond rest and more negative. Now, I mentioned action potentials before, but there's also something called graded potentials. Graded potentials are local changes. I have here chemical, light, heat, mechanical. A lot of things can cause it. But graded potentials can only occur in a small area, and they really can't spread very far. So that's where the whole idea of action potential comes in. They spread far. Graded is localized, very small areas. They're short-lived. You can't just keep regenerating it like an action potential. So graded potential happens. If it can add to another one, great. If not, it just dissipates out and goes. So localized events, short-lived, graded potentials. Now, these graded potentials can be stronger or weaker. They're not a set amount. It depends on the stimulus that triggered it. So therefore, you could have 2 or 3 strong graded potentials might be able to trigger an action potential. Or maybe you need 6, 7, or 8 weaker graded potentials to trigger an action potential. The idea is the goal of the graded potential is to create some event from the stimulus that was received. If those graded potentials can reach threshold by adding together or summate, if they add together or summate to reach threshold, they can trigger an action potential. But these graded potentials by themselves can't do a whole lot. They're small, localized events. These graded potentials, more often than not, are based on chemically gated channels. We've seen that at the neuromuscular junction. The acetylcholine binds to a channel, opening up that chemically gated channel. That was a graded potential that's being created then. So these graded potentials, well, we've already talked about them as far as depolarizing, -70, -69, -68, -67, but they can also hyperpolarize. If the neurotransmitter, or the receptor for that matter, are meant to trigger a hyperpolarization, it goes the opposite way. It goes beyond the resting state. So as I said, example, the neuromuscular junction, chemically gated sodium channels there. So as that works, opens up, sodium rushes through, create this graded event. If enough of it binds, and you have enough of these channels adding together, you might reach an action potential. So I keep mentioning action potential because that is the main signal mechanism of your nervous system. Action potentials can travel long distances. Action potentials are only found, though, in muscles and neurons. That's it. So the only 2 types of cells. But what's interesting is they do not decrease in strength over time. So no matter how far this action potential is traveling, it will maintain the exact same strength all the way down the entire neuron or muscle. That's because they keep being regenerated as they travel. More and more channels open, more and more ions flow. They're constantly being regenerated. And that really is how your nervous system, and for that matter your muscles, are sending signals. They're sending signals as action potentials. So graded potentials, action potentials, depolarization, repolarization, hyperpolarization, the different ways the nervous system and the muscular system for that matter can communicate.